polynomials. If p of x is a polynomial function, then the limit of x goes to a of p of x is p of a. That's basically saying that all polynomials are continuous. All right, it doesn't have to give a caveat about the domain, because the domain for any polynomial is all real numbers anyway. So this is saying, now that we have the context of what continuity is, we know that definition, this is saying that all polynomials are continuous. If you think about it, any polynomial you can draw is like, here's a quadratic, here's a parabola, right? Here's a cubic. They're one smooth curve, right? You can draw it in one motion. And then also, oops, let me switch this here. Doesn't want to. There we go. Any rational function. Now this caveat here, as long as d of a is not equal to 0, well, if a makes the bottom 0, then a is not in the domain, right? So this caveat is similar. It's effectively saying if a is in the domain. So we could have rephrased this. Instead of referring to the denominator, which I wanted to do to be more specific because we're focusing on the denominator in these examples, but you could rephrase this as if a is in the domain, then such and such. So this is also saying all rational functions are continuous at all the points in their domain, all the numbers in their domain. So now that we have what continuity is, these, if we go back and look at them, imply continuity for those function types. The limit as x goes to 5 of secant x, well, that's just secant of 5. Okay, whatever that number is. Okay, because 5 is in the domain of secant. 5 is not a multiple, an odd multiple of pi, I think it would be. Is that right? Yeah, an odd multiple of pi. I'm sorry, odd multiple of pi over 2. 5 is not an odd multiple of pi over 2. So we know that's in the domain. Therefore, I just plug it in, which is what we said before. Now we're just giving it the context of continuity. So if I wanted to look at another example like this one, say the limit as x goes to 0 of sine of 1 over x. Right? We drew this one out before. Close enough. Then this one looks like something like this. Okay, and then like that, right? So this is called an oscillating discontinuity. This one doesn't show up that much. In fact, item 1 fails. And really all 3 fail for this one. Item 1 fails, item 2 fails, because the two-side limit doesn't exist. So of course, since 1 and 2 both fail, 3 has to fail. But 1 and 2 both fail in this case. In this case, item 2 passes. The limit does exist. It's just not a number. Item 1 fails only. For this one, item 1 passes. The function is defined. Item 2 fails. I say only. If either 1 or 2 fail, 3 automatically fails. So I mean between 1 and 2. Here, 1 passes, 2 fails. Here, 1 fails, 2 passes. Here, 1 passes and 2 passes, but 3 fails. So typically you only have one of either item 1 or item 2 failing. It depends. In this case, you have both item 1 and 2 failing. Okay, both the function does not exist and the limit does not exist. So how would you investigate problems? They're a little bit different from this one. So let's say this one. I mean, let's go back to this. Let's revisit one we've already done. If I have f of x equals x squared minus 4 over x minus 2, right? I could ask, is this continuous? For one, is it continuous on its entire domain? Well, yes, it's a rational function. So this is continuous on its domain. It's continuous on its domain. Okay. But 2 is not in the domain, right? So it fails item 1. So if x equals 2, then item 1 fails. Okay. And in fact, what I should be saying, since I'm writing this out in sentences, I should say item or point 1 of the continuity test, which I didn't, I didn't write up here. This is often called the continuity test at a point. Continuity test at a point. Or the test for continuity at a point, however you want to phrase it. So item 1 of the continuity test fails. Okay, so what kind of discontinuity is it, right? Here, when item 1 fails, we have infinite. Here, when item 1 fails, we have removable. So which one is it, right? We don't have a graph to look at. Now, you could type it into a graphing calculator or something and look at it. We don't have that capability. So I need to check, does item 2 pass, all right? Is this removable or not, right? This one, well, this one, item 2 passes, but you get infinity. This one, item 2 passes, and you get a number. That will tell me the distinguishing, that will distinguish between the two. Is the two-sided limit infinity or something else? So we've already worked out what this two-sided limit is. We've done it before. The limit as x goes to 2 of x squared minus 4 over x minus 2. Well, that equals the limit as x goes to 2 of the top factors, x minus 2 times x plus 2 over x minus 2. So those factors cancel. And I get that this equals the limit as x goes to 2 of x plus 2, which is 4. I got a number that way. So this leads into something that's called continuous extension at a point. I don't think the homework is going to ask you to reproduce this kind of thing. I can check that real quick. I don't think that it does. Let me look. I also talk about it, but if it's not on the homework, I won't do as many examples of it. The homework definitely asks you to identify which items in the test fail to be met. Yeah, okay. So item 2 fails. Oh, and in the homework, there's not called item 1, 2, 3. It's like the statement of the continuity test is given, and you're identifying which ones are failing. You don't have to, for the homework, you have to memorize these. For a test, I'm not going to necessarily give you, here's the continuity test, tell me which items fail. You'll have to know the 3 parts, but the homework problems do cite them in the problem. So item 2 fails. I'm sorry, not fails. Passes. Sorry, passes. Okay, so this is a removable discontinuity. And that's because I got a number for the two-sided limit. Now, it's called removable, as I said before, because, you can repair that gap in the graph. What this means is that this graph, I guess I scroll down, looks something like this. Oops. There's a little gap in the graph. Okay? So, and that's at x equals 2, y equals 4. My graph is a little wonky, but we'll just go with it. So if I fill in the graph and say, no. If I say f of 2 equals 4, then I can repair that hole. I can define a new function, g of x. And this function equals x squared minus 4 over x minus 2 whenever x is not equal to 2. And then it's 4 when x is equal to 2. I can redefine the function in terms of a piecewise function and fill in that gap. this function is continuous because I've said, okay, there's removable discontinuity. Well, let's fill in the gap. Let's say when x is 2, just use 4 instead, and don't worry about the rational function, right? Because that's the limit that we got. That's why I say this is what the function should be doing. That's why I used that term should before, because it means, oh, I can fix the graph, and now it is continuous, okay? Another way to write this, based on what we have here, some of you might be thinking it already. Can anyone see of a cleaner, neater way to write this function instead of having it piecewise like this? Here's a big hint. It's on the screen right now.
Are you saying use an inequality?
No, no, no. I want to write g of x equals some function. And
Is it x plus 2?
it is. It's x plus 2. So x plus 2 is a continuous. It's like a repaired version of this function here. X squared minus 4 over x minus 2 is a function. It's a rational function. It has a domain. It has a range. And 2 is not in the domain. But it can be repaired by filling in that gap, and you just get this straight line with slope 1 and y-intercept 2. X plus 2, right?